This video is a solution to the power example problem. A 2,800 kilogram car exerts a constant force of 20,000 newtons while traveling across 50 meters. The car starts from rest. A. How much work is done? B. How much power is exerted by the car? So let's look at this problem in terms of the givens. What do I know? Well, I'm given the fact that the mass is 2,800 kilograms, and I'm given that the car starts from rest, so that means initial velocity is 0. I'm given that it travels a distance of 50 meters, and it has this force parallel to the motion, or parallel to the displacement, that's equal to 20,000 newtons. Part A says how much work is done. Well, there are lots of ways to find work, but when I look at this list, I can see I've got force and I've got distance. So that's the way I'm going to choose. Work is equal to force parallel, that's because the force of the car is in the same direction of the motion, times the distance. So that's 20,000 newtons times 50 meters, or 1 million joules. So this car does 1 million joules of work. Alright, next, how much power is exerted by the car? Alright, so power. I need a little bit of a strategy here because it's not so obvious. Power is work over time, and it's the change in energy over time. There are a couple ways I can do this, but here's the strategy I'm going to go with. I'm going to calculate the time using kinematics and Newton's second law of motion. And then once I have that time, then I'll use the fact that power is equal to work over time. So that's my strategy. Find the time with kinematics and Newton's second law, and then use work over time to actually calculate the power. So kinematics. These were my old kinematics equations. And Newton's second law. So when I'm looking at this, I'm thinking, alright, I need to find the time. To find the time, I really need the velocity, the final velocity. But to find the final velocity, I've got to find an acceleration. So that's where the Newton's second law, the use of Newton's second law comes in. So I'm going to use F equals ma to find the acceleration. So 20,000 is equal to 2,800 times a, and that gives me 7.14. So there are a few more decimals I'm not showing, but for the sake of space. But 7.14 meters per second squared is the acceleration. Now I can use that in my long kinematics equation, the x equals x naught plus v naught t plus 1 f a t squared, in order to find the time. So that's what I'm going to do with that. Instead of finding the final velocity, I'm going to go for the time here, a little change of plan. So using the long equation, I got 50 meters is equal to 0, and it starts at rest, so that's 0 plus 1/2 the acceleration with all the decimals, times t squared, and that gives me the time of 3.741657387 seconds. Next step, power. Finally, to answer the question, power is work over time. The work was 1 million joules, and the time is 3.74. So power is 1 million divided by 3.74. When I do the math, I get the power to be 267,261 watts, which is a little more than 300 horsepower. So a pretty powerful car.